we're going to finish up talking about weak acids, and then we'll talk about some percent dissociation, and then we'll talk about weak bases. So if I have a mixture of weak acids and you're asked about the pH, the process is exactly the same. The trick you have to know is that the stronger will dominate the reaction. So the one that has a bigger Ka, the bigger the Ka, the stronger the acid, is the one that is going to contribute the most of the hydrogen ions, which is what's going to affect the pH the most. So if we're trying to calculate a mixture of HF and our other one here, HC or HOC6H5, then what we're really going to look at, we want to focus our efforts on the strongest one. The Ka for HF is gigantic compared to the Ka. This is times 10 to the negative 10 of that other one. So it is going to be HF that is affecting the pH the most, and so really you're going to do your icebox based only off of HF. Now it is a weak acid there, so you would have to go through the whole process with that icebox, putting your 1.20 here and here, and then you can finish that problem on out if you'd like to. I did get a pH of that one of 1.53. 1.532 was my pH for that particular problem. So you can work that out if you'd like to. All right, let's talk about percent dissociation. It's the amount dissociated, how much of this weak acid actually split up over the initial concentration times 100. And for weak acids, the percent dissociation increases as the acid becomes more dilute. And to prove that point, I have these two problems here. If it's a 1 molar acetic acid solution and if it's a 0.001 molar acetic acid solution. So here it's going to be very much the same. We're going to do an icebox. Let's just do it with the 1 molar acetic acid solution first. So I'm going to have HC2H3O2, and it's going to split up and get back together. These acetate ions. And I have a 1 molar concentration. At the beginning, I have no ions, and then that is going to change. I want to see how many ions. I don't know, so I'm going to make it X, and then I'll move my X all over, minus X. This is 1 minus X. This is X here, and then we can plug that into our Ka. So 1.8 times 10 to the negative 5. Products over reactants, so that's going to be X squared over 1 minus X, but again, X is going to be tiny because this is a very small K, so X in relationship to 1 is going to be too tiny to really make a difference. And then if I solve for X, I end up with X being 0.00424. Now, to find that is the amount of ions that I got. That is how much of that acetic acid actually split up. And actually, if you look right here, you can see X is how much actually split up from the initial concentration. So that's the number I'm going to use for the amount dissociated. Not X squared, just X. Because the other one is going to be the exact same amount, and that is just how much split up. All right, so then if I do 0.00424 divided by my initial concentration, which is 1, and then times 100, I end up with a percent dissociation of 0.42%. Alright, so only 0.42% of a 1 molar solution will actually dissociate into its ions. Now, if I go through and modify this icebox a little bit for the other one where it's 0.001, and so we can change this one here, 0.001, and we'll just move our decimal here, and then we can plug it in over here. 0.001 minus X. Again, X is going to be tiny in comparison to another number, so we're going to simplify that. And in this case, for this particular problem, you're going to end up with X equaling, let's see, okay, .0000134 is X. And again, if I put, that's the amount that is dissociated, 0.0000134 over 0.001, because that's initially how much I had, times 100, then I am going to end up with 13% dissociation. So that's how you can work with percent dissociation. I could also do that the other way and go from percent dissociation to a Ka. It's just flipped around here, so 8.1% equals the amount of the ions, which I've been calling X, over the initial concentration. The initial concentration in this one is 0.1. And that would have to be times 100. So divide both sides by 100 and you end up with 0.081 equals X over 0.1. And then X is going to be 0.0081. Now to find the Ka, I've got to find those equilibrium concentrations. So it's some sort of acid, some sort of weak acid. It's going to split up and get back together. I start off with 0.1 of this and nothing of these initially. Change and equilibrium. At equilibrium, I'm going to have X of both of these. And over here, it's going to be 0.1 minus X. And so now that I know what X is, I can plug it into my Ka, which is going to be products over reactants. So H plus times A negative concentrations over the concentration of my acid. And now it's just going to be X is 0.0081 times 0.0081 over 0.1 minus 0.0081. And figuring that out, my Ka is going to be 7.1 times 10 to the negative 4. Sorry, not more. It's just my Ka. Alright, so that's working with percent dissociation. It takes a little bit of practice. Once you get the hang of the ice boxes, it's really not very difficult. Alright, now let's talk bases. Again, it's going to be more of the same. Bases are done a lot like acids, just a little bit of a trick, especially if you're trying to find the pH, because you have to go through pOH. Hydroxide's a strong base. Alkali metals are strong bases because they dissociate completely. Alkaline earth metals like calcium hydroxide are strong basic bases, but they don't dissolve well in water. So often they are used as an acids because you won't get too much hydroxide in your system, which can cause the pH of your blood to be lowered or increased, and once it gets outside of its range, you end up with major organ failure, so we don't want that to happen. So that's why they use the ones that don't dissolve well in water. Alright, bases without hydroxide are probably going to be weak. Your weak base that you need to make sure you know is ammonia. Now we might end up with some organic substances, and it might have a whole bunch of C's and H's, but at the end it's got something that looks like this. If it looks like ammonia, it acts like ammonia, and it's going to steal a hydrogen. That's what these types of things do. So don't let that freak you out. If it ends with NH2 or just NH, it's probably going to steal a hydrogen when it interacts with pretty much anything. And here I just have the interaction of ammonia and water. And it is weak, so it does keep going back and forth. Here, if we signify a base, it's just B, base plus water. The base is going to pull a hydrogen off of the water and will look something like this. And then you're left with those hydroxide ions. When we write the Kb for that, it is products over reactants raised to their coefficient power. Would not leave water in because it is a liquid, just like the other one. Alright, so hydroxides are strong, everything else is weak. Smaller Kb, the weaker the base. And they want us to calculate the pH of pyridine. So what I'm going to do here is pretty much the exact same thing. And I have my, I'm going to write my equation here. So I have my pyridine, I'm just going to represent it by a P, plus H2O. And it is going to steal a hydrogen and become pH plus. And water will be left with OH negative. Alright. Now what I'm going to do is I'm really going to ignore water. It doesn't enter into my equilibrium expression. So I'm just going to really just kind of ignore it in my icebox. Initially, I have point or 4.0 molar solution of the pyridine, and at the beginning there's no interaction with the water, so I have none of those other ions. But there will be interaction with the water. How much? I'm not quite sure, so we're going to make that equilibrium expression x, which makes my change plus x. And then I'm going to move my change across, so that's plus x, this is plus x. And go across the great divides. This is a weak base, and this is going to be minus x. So this is going to be 4 minus x. I'm going to set this up in my KB. KB is going to be products over reactants, so it is going to be my ions here, the hydroxide ion, over the pyridine concentration. And so now I'm just going to plug these in so I can solve for x. 1.7 times 10 to the negative 9 equals x times x over 4 minus x. But again, since k is really, really small, x is going to, we're going to be able to simplify that. X is going to be small in comparison to the 4. So we'll simplify, and with that, I end up with x being 8.2 times 10 to the negative 5. That is my hydroxide ion concentration. That's the one I'm interested in because, again, I want to find the pH. Well, if I take the negative log of my hydroxide ion concentration, I don't get pH, I get POH, but I can use it to find pH. So I end up with 4.08 as my POH, and then 14 minus that gives me my pH of 9.92. So this is very basic, and we would expect that out of the base. But that's how you are going to find your pH for weak bases.